In this video I will demonstrate how to use a slide rule to calculate exponential growth. As a guide I will be using a spreadsheet to better show the steps involved and then use a slide rule to perform the same operations and hopefully come to the same answers. For our example we'll be using the cases of coronavirus infections in the United States to calculate the number of infections at a given time. The formula uses the principle of applying a fixed rate of growth to a known quantity at some time in the past to calculate the quantity at some time in the future. The Wikipedia website on exponential growth is a great resource on better understanding where exponential growth can occur and how it can be calculated. A bit further down the page is the basic formula for calculating exponential growth, and this is the one we'll be using. In the spreadsheet that I prepared earlier, I'll be using slightly different letters, but the principle of the formula is the same. This is our spreadsheet with the exponential growth formula, and we'll be using this as our guide. Feel free to pause the video at any time to better understand what's going on. In order for us to calculate the number of infections at a given time, we need to calculate the growth rate number first. Fortunately, we make use of the freely available historic coronavirus data on the Worldometer website. By hovering our mouse over the graph for a certain date, we can see the number of infections. When I made this video, I only had data up until the 10th of April. Looking at the graph, I decided to use the number of infections on the 1st of April as the start quantity and the number of infections on the 10th of April, being 9 days later, as the end quantity. Using the exponential growth formula, we can now calculate the growth rate. So on the 1st of April we have 216,000. This is 1 day later, 2 days later, 3 days later, 4, 5, 6, 7, 8, 9. So after 9 days we have 502,000. So now we can enter those values in our spreadsheet. For the start quantity we have 216,000 and we use 502,000 for the end quantity, which is after 9 days. Get rid of that. Before we dive into the calculation for growth rate, let's just see what the number of infections would be in 7 days from now. When we enter 7 as the time period, we are counting from the start, which is the 1st of April. So day 7 was actually 2 days ago, and today is day 9. So if the 9th period is today, then 7 days from now is 9 plus 7, and that's 16. And we see that the calculated number of infections is just under 1 million. Let's see if we can get above 1 million on day 17, and we do. So back to calculating the growth rate number. The spreadsheet already shows how to get to the answer, but I'll briefly explain how we get there. Because we just grabbed the values from the Worldometer website for the 1st of April and 9 days later, and Euler's number is known, there's only one unknown to work out, and that's the growth rate k. Adding the numbers in the formula, it becomes clear that only k is unknown. We simplify the formula by removing the 216,000 multiplier by dividing both sides with it. That then just leaves us with e to the power of 9 times the growth rate on the right of the equal sign. The last step will then be to undo the e to the power bit by taking the natural logarithm of both sides. So dividing 502,000 by 216,000 will give us 2.3 something, and we end up with just the e to the power bit on the right. We can now take the natural logarithm of both sides, and that will leave us with just 9 times k on the right side of the equal sign. It's then simply a matter of dividing the left portion by 9 and we get our growth rate. As you can see, the calculated growth rate for these numbers is about 0.0935. The real growth rate in our coronavirus example is not a fixed number. It changes from day to day depending on various factors. None of these are taken into account in our basic formula. Let's assume that it is constant and we wish to calculate the number for day 17. Here, y for period 17 is unknown, and we need to work out everything on the right side of the equal sign. Fortunately, all the numbers on that side are now known. When we plug in the numbers, we use the start quantity of 216,000, Euler's number, and work out the exponent. When we multiply the growth rate times 17, we get about 1.59. We then take e to the power of 1.59 and multiply it by 216,000, and this will give us 1,063,000. As said, all of this is based on a fixed growth rate using the values from the 1st of April and 9 days later on the 10th of April. Now let's see if we can use a slide rule to make these calculations. The slide rule that I'll be using is a Sun Hemmi P280. It's a really nice plastic slide rule, and what you would need is the C and D scale and the log 1, 2 and 3 bars as well. We'll need both, and how to use them I'll show you here. So based on the formulas that we have calculated here, let's just take that step by step. Let's first see if we can calculate the growth rate number, because that'll be a starting point. So the blue bit in the middle is adjustable. It slides, and the top and bottom whiter bits are the frame of the slide rule, and it stays in place. And the idea is to line up the numbers that you're interested in and then read off the result. So the C and the D are pretty much the same. There's a few other markings on there, but they are normal logarithmic functions, and or a logarithmic scale from 1 to 10. And the way to use that, we'll just show you that as we go. So first of all, we need to see how we can get the growth rate number. And so what we see is that we have to divide by the beginning rate. So the 216,000 is the start rate, and 502,000 is after 9 days. So we need to divide 502 by 216,000. Well, 502,000 by 216,000. The funny thing with slide rules is that you're always trying to find out where the decimal point goes, but in this case, since the numbers are very close in orders of magnitude, we can just get an idea of where the answer needs to be. So 5, that's 550, we need 502, so that is 510, and that's 505, and we need 502, which is sort of there-ish. Yep, just a little bit to the right of 5. Now to divide by 216, we need to bring in the blue bar the number 216 above that 5.02. So 216, so that's 3, 2.5, 2.4, a bit further, 2.3, 2.2, 2.1, and we need 216, 2468, 1222, 246, 216 we have here. So now that we have lined up those, the white and the blue, we can read from the beginning of the scale, or at the end, depends on how it falls. Where that 1 is on the C scale, we can now read off the answer, and our answer is just above 2, so we'll have to sort of look around, how do we interpret that number, and if that's 2 and that's 3, and 2.5, 2.4, 2.3, 2.32 and a bit, you can see that it just goes over 2.3 and then 2 and a bit, and what we're expecting is 2.32 and a bit. So that all makes sense. 500 divided by 216, they're sort of in the same league, so we get an answer of about twice, and that makes sense. So doing it with the slide rule, we get pretty close. We can definitely get 2.32 out of there, and that's good. So next thing is to take the natural logarithm to undo the e, Euler's number. So we need the natural logarithm of that 2.32, and for that we need the log scale. So I'm just going to slide that out, flip it over, and then insert it. And here you have log 1, 2, and 3, and they are just from small to very large numbers, and depending on which one you need, you'll read it off the various scales. So at the beginning of the index, we'll just align the E, Euler's number, above 1, because those are the scales we're interested in. Yeah, up there. And the number we're interested in was 2.32. So that is a number that is a whole number. So the EX scale, which is the log 3 scale. Sorry, no. The number is 2.32, and we can find that on the scales, and it just happens to be on the log 2 scale. So 2.3 would be 1, 2, 3, 2.32, sort of in there. We'll bring in our marker here, so you can actually align that and then read it off. So bring in the marker now. So that's 2.1, 2.2, 2.3, and we need 2.12, 2.321, 2.123, 2, and a little bit. Well, that's sort of just a whisker to the right of that mark. So that's 2.321, and we look down then on the wide scale, and we see something around 8.5, 8.4, 8.41, sort of there, and that's what we're getting here, 8.42. So that's reasonably close. The next thing is to divide it by the number of periods, in this case 9 days. So 0.8, we need to divide that by 9, and that's almost like a divide by 10, so the comma should shift a little, and we should be close to our 0.9 and add an extra 0 in there. That is a division, so we'll need the normal, the C scale again. So we'll just flip that middle part over and use the C scale to read that. We'll just leave the marker as it is in place. We don't have to move that. So it's still at 8.41. Now for division, we need to bring the number that we divide by above it, and then we read it off the beginning or the end of the index of the scale. So 0.8 divided by 9 is, and where that last mark is on the 10, we read down and we see something like 9.123, 9.35, somewhere there, 9.35, and we should be getting 9.357. So yeah, all of that is pretty good with a slide rule. You're pretty close to getting accurate numbers. So the next thing is to use the growth rate and see if we can come up with this 1 million number. So now that we have the growth rate, we multiply that by 17. So the growth rate is 0.09, and with the growth rate of 0.09, we multiply that by the future number of periods. So we're interested in period number 17. That's 1 week from now. 1 week and 1 day, I think. Multiplying that, we should get around 1.5. So the marker is still at 9.35. Multiplying, we can still do that on the C scale in the blue. So we just multiply that by putting the marker at where it is. Basically, we don't have to touch anything. Multiplication, we just read it off where we want to multiply it by, and in that case we multiply it by 17. So this is 1, 11, 12, 13, 14, 15, 16, 17 in the blue. So bring our marker here, 17. Is that 5.9, sort of there, somewhere there, 1.59, and that's sort of 1.591 is the expected answer. So that's pretty good. So the next thing is to bring that along on the log-log scale. And so what we do is we need to raise e to the power of 1.59, and again, because it's the Euler's number, we use the log-log scale to read that number off. We don't have to move the index. We'll just leave that where it is. We'll just swap over to the log-log scales, and then the number still being set on the D scale to 1.59. We'll be looking at Euler's number, so we'll align the E with the 1. There you have it. And so what we do now is the number 1.5 is a number that we can use straight away. There's no multiplication involved. It's not 15, it's not 0.15, so it's just a whole number times 1. And so for that is the bottom rule, log 3. And when we then look at our red line 5.9 and we go up, we see on the log 3 scale a value close to the expected one of 4.9001, I think it was. So again, the slide rule is pretty good at helping us with that. At the end of the scales, that's what I was going to say. At the end of the scales, you can see that e to the power of x, if x is a whole number, then you use log 3. If it's less than that, you can use log 2 and 1 for that. So just reading off that 5.9 on the log 3 scale, we can see that the answer is about 4.9 and a bit. So again, when we use that in our formula to calculate the total number of cases, I'll bring it a little bit better in view here. We can see that we need to now multiply that times 216,000. So 4 times 200 gives you a bit of a ballpark as to how big that number is going to be. The number was read on the log 3 scale at 4.9. We'll have to set that again on another scale. It doesn't always, well, in between apostrophes, remember that, but you have to sometimes remember these numbers. So here we set it back on the C and D scale, 4.9 and a bit. And for a multiplication, we just bring the end of the slide above where it needs to be. So here's 4.9. We bring the end of the index there, and a bit more. 4.9 and a bit. There you go. Good enough. And then we multiply that by 216. So that's 4, 3. And 216, 216, 2, 5, 1, 246. So that's 216, 216,000. So we bring our marker there, 2.1, 2.2, 2.4, 2.6, sorry, 2.16, and then down below we can then read off between well, the one on the left is 1 million. The other one is 1,100,000. So we see 1 million sort of 0.6, yeah, sort of 1,060,000. And that brings us right in line with what we expected here. So it's nice to see that you can use the good old slide rule for these basic exponential functions. Hope you enjoyed it.